Hello everyone, and welcome to my first example problem video that will be covering problems from section 1.6. In this video, I'm going to be going over a differential equation problem that requires you to use the method of substitution in order to turn the differential equation into one of a previous kind that we've learned how to solve, which means that we're turning this, hopefully, into something that's either separable or first-order linear. Now the problem I'm going to be showing you guys today is the very first problem from the homework in the book in section 1.6. And I want to point out from the get-go that this is not a problem that is, at first glance at least, homogeneous. I'll be addressing the homogeneous type problems in a future video, but this one we are going to solve with a judicious choice of substitution. Let's begin by recalling the goal of a substitution method. The goal is very straightforward. We want to turn the differential equation into one of a type that we know how to solve and in our case that means basically just separable or first order linear by making a variable substitution. Usually, we use v as our new variable. And a quick note here. After all substitutions are performed, we want all the y's and dy's, etc., to be gone. So we only have an equation with v's and perhaps x's. Alright, so with this in mind, let's tackle the problem that I have written out at the top over here. The differential equation that we're working with here is x plus y in parentheses times y prime, or dy dx if you prefer, is equal to, on the right-hand side, x minus y. Now the first step that we're going to have to perform here is that we are going to have to choose a substitution. And keep in mind, in practice, some trial and error may be required here. So don't worry too much if you don't pick a perfect substitution right in the get-go. If your substitution doesn't work out, if it sort of seems to lead you to a dead end, come back here, see if you can think of a different substitution to try, and see if you can try and make that work. Alright. Once you have chosen this substitution, I want you guys, specifically if this is on an exam, but I recommend doing this in general when you're solving these problems, because good bookkeeping means that you'll perform, or you'll make fewer mistakes, rather. I want you to write out the substitution. So write the substitution. You use out. All right, so in this problem, right off the bat, we can see that there are sort of two different clumps, I would say, that, at least to me, sort of jump off of the screen or of the paper as being possible candidates for substitution. The first would be this clump over here, this x plus y, which is in parentheses, which is multiplying our y prime. If we could replace that with just a v, that might be kind of nice. The second one that is a possibility, at least that jumps off to me as a possibility, would be this right-hand side rather over here, x minus y, is also, I think, a sort of tempting candidate. That doesn't mean that these are guaranteed to be the correct substitution to make every time. In some cases, for some problems, there may not be an obvious substitution. You might not have some immediate candidates. And in those cases, I'd recommend sort of manipulating the equation algebraically a bit. First, see if you can get things to cancel out. Maybe move this stuff in front of the y prime over to the right-hand side. Fiddle with it a bit, see if you can, find some sort of pattern or something that's promising. Again, don't worry if it takes you a couple of tries, if you don't pick a perfect substitution right off the bat. Some trial and error should hopefully get you there. Okay, in this case, I must admit I have not tried the substitution v equals x minus y. I suspect that there's maybe a reasonable possibility that might work out. But what I'm going to use in our problem today is the substitution v equals x plus y. So again, I want to remind you guys, write this out. That includes on the exam, I want you to write out your substitution. If you wish to get full credit, that is. All right, step 2. Write what both y and dy dx are equal to with the substitution you chose. And a quick note, as you might recall in class, I made a point of going back over chain rule, and that is because chain, product, and or quotient rule may be needed to get dy dx. All right. For some of you, it might not be exactly immediately clear what I mean by saying writing out what y and dy dx are equal to with the substitution that you chose. So let's move these out of the way, and I will demonstrate with the current problem what I mean by that. All right. So in step 2 in this case, this is continuing step 2, we have since v is equal to x plus y, we have therefore that y is equal to v minus x. This is what I mean by writing, when I said write what y is equal to with the substitution I chose, is just flip this initial guy, your substitution equation, around to get y on the left-hand side. All I did was manipulate the simple equation. Now, how do you get what dy dx is equal to? Simply take derivatives. Taking derivatives yields that dy dx is equal to the derivative with respect to x of v minus x. Now we know that derivatives are additive, so the derivative of v minus x is the derivative of v minus the derivative of x. So this is equal to dv dx minus dx dx. And of course dx dx is just equal to 1. So in other words, what we've gotten is that dy dx is equal to dv dx minus 1. Now when I wrote write what y is equal to, I meant write this guy out. And when I wrote write what dy dx is equal to, I meant get this guy. Hopefully you guys are still following. At this point, we still have not performed any substitutions. Please note that we still have not actually used anything from this starting differential equation. All I've done so far is I've chosen a substitution, and I've fiddled with that substitution that I used to find the equation in my substitution of y and one for dy dx. Once this is done, once you've written all this out, and again I want to see all of this very clearly on your paper when you're when you're submitting an exam, next we can proceed with actually substituting in these new variables. All right, I'm going to move things around, and then we're going to proceed. Okay. Oops. Using the pencil rather than pen. All right. So now we move on to step 3. Step 3 is perform the substitution. All right, so when I make these videos, I like to color code my substitutions for clarity. So over here in this initial equation, what I have boxed in blue is, as you can see, exactly our substitution for v. Now over here on the right-hand side, you can see that we have a y, which I'm going to box in green, because we've already boxed our value of y in green further down below. We see that y is going to be equal to v minus x. Last but not least, in red, I'm going to box this y prime. And y prime, which is dy dx, of course, we boxed in red. We said that dy dx is equal to dv dx minus 1. Now at this point, I'm going to substitute all of these in, basically all at once. Okay, so first off, we're going to have that x plus y in the blue box is going to become v. This is being multiplied by, and do not forget the parentheses here, we're going to have dv dx minus 1 in these parentheses, and this is what was boxed in red. This is what we said that dy dx is equal to. Now back over here on the right-hand side, this x minus do not move. They're still exactly the way that we placed them there originally. But the y, which we have boxed in green, is now going to be replaced by v minus x. And again, do not forget your parentheses. All right. Hopefully this color coding is helpful, and hopefully you guys can all see exactly what I substituted here. Also at this point, ideally you guys can sort of see why I emphasize that you should write out not just your substitution, your choice of v, but also write what that means your y is going to be equal to, and what that means your dy dx is going to be equal to. If you write all three of those things down, and again that's what I've got boxed in blue, in green, and in red over here next to step 2. Once you have all those written down, performing the substitution itself is very simple, and you're much less likely to make any mistakes. Okay, it's time to do a little bit of algebra. Let's simplify things a little bit over here. So first off, we're going to leave this over here the same. We have v times dv dx minus 1. And over here on the right-hand side, let's simplify this. You can see that distributing out the negative sign and combining things together, we will get that the right-hand side is now 2x minus v. All right, now we're going to pass this v from the left-hand side over to the right-hand side by dividing everywhere by v. So we're going to get dv dx minus 1 is equal to 2x divided by v minus v divided by v. In other words, we're going to have that dv dx minus 1 is equal to 2x over v minus 1. And this is going to give us, finally, that dv dx is equal to 2 times x over v. Now I'm going to box this guy sort of lightly in yellow here, just to emphasize that this is now our new differential equation. And this is now what we're going to be trying to solve. So instead of solving that initial differential equation that we started off with, which didn't really look like anything of the type that we know how to resolve, we performed this substitution. We set v is equal to x plus y. We fiddled with that to determine, based off of that substitution, what we're going to need to substitute in for y and what we're going to need to substitute in for dy dx. And after substituting all of this, we have this new differential equation. And you can see, as I said in this note below the goal up here, I said that after all substitutions are performed, we want all the y's and dy's and anything where y comes up to be completely gone and to have only an equation with v's and with x's. You can see that we have that here. We have dv dx is equal to 2x over v. There are only v's and x's here. There are no y's to be found. All right, now speaking of that goal, our whiteboard here is getting a little bit crowded. So I'm going to get rid of that and move everything that we just did a little bit further up here. Okay. So now that we've gotten our new differential equation, we're going to move on to step 4, which is very simply solve this new differential equation. And if you've chosen the correct substitution and performed all the previous steps correctly, at this point, you should have something separable or perhaps first order linear. And you can see that we have dv dx is equal to 2x over v. And you'll see immediately that this is separable. We can separate these variables in a very straightforward fashion. And so we're just going to do that, and then we're going to solve this exactly the same way as we'd solve any separable differential equation. All right, so this is again getting a little bit crowded, so I'm going to move this up here. All right, as I said, this equation is separable, so now we simply separate the variables. And this is going to yield the following. And all I'm doing here is I'm passing all of everything that has a v in it to the left-hand side, and everything that has an x in it to the right-hand side. And you can see that this is going to give me that v dv is equal to 2x dx. Now we simply integrate. To get that the integral of v dv is equal to the integral of 2x dx. And the integral of v dv is going to be 1/2 of v squared. And the integral of 2x dx is going to be equal to x squared plus c. Okay, I'm going to move this up a little bit just to do the final step of what I want to do here, which is to see that this is therefore going to give us that v squared is equal to 2x squared plus c. Now some of you might ask, shouldn't that be plus 2c? Well, keep in mind that 2 times a constant is still a constant, so we really don't have to go through all the trouble of writing 2c in front of that every single time. Okay, now the other thing that you might be asking here is, shouldn't we do something about that v squared? Now, technically speaking, we could. We could take square roots of both sides, but we need to keep in mind that we'd have a plus or minus square root on the right-hand side, and we don't really like having to make big messes here. And since in either case we're still going to have to substitute our original variable back in, let's just leave things as is here. In other words, don't make too much of a mess in this part, because you still need to substitute back in the final step. Now let's proceed and do exactly that to finish off this problem. So this is moving on to step 5. Substitute the initial variable, or in this case just the y, back in. Now to go back to our color coding, we had written initially that v, which is this guy right here, is equal to x plus y. So we're just going to substitute that right in, and we're going to get x plus y, in parentheses, don't forget those, squared, is equal to 2x squared plus c. And to keep up with my color coding, this x plus y in parens is exactly what I have boxed in blue. All right, now we simply simplify this a little bit. Frankly, in this type of problem, in a sense, you've already solved the equation implicitly, but it's worth going a little bit further, even just to see whether or not you can get an explicit solution here. So in this case, we're going to get that, oh, wrong color. Let's cancel that, switch the colors back. In this case, we're going to see that we're going to get that x squared plus 2xy plus y squared is equal to 2x squared plus c. Now we still have this y squared in there. We're not going to really be able to get rid of that in any sort of meaningful or helpful way. So basically what I'm trying to say is we're not going to be able to get an explicit solution, just a y is equal to something on the right-hand side here. But implicit solutions are nice. So a quick note, at this point in time on an exam, you could leave your answer like this, and I would give you full credit because this is an implicit solution. I mean, obviously it'd be nice if you passed the 2x squared back over and simplified that, but even that's not necessary. However, on the homework set, specifically on homework assignment, on the homework set 3 that I posted this last week, they do expect you to present these implicit solutions in a specific format. So I'm going to quickly show you what format they expect for this type of problem. And that basically means that what they want you to do is leave the c, the constant, all alone on the right-hand side, and have everything else over on the left-hand side, and I think they probably want it as simplified as possible. So let's see what we get when we do that. All right, let's move this guy over here and just make the quick final note. So on the homework, a standard form, or a format if you prefer, is often expected for implicit solutions. simply keep the c alone on the right-hand side. Everything else to the left-hand side. And doing so gives that we will have negative x squared. That's our x squared minus the 2x squared that we're subtracting, plus 2xy plus y squared is equal to c. Alternatively, if you don't really like having the negative in front of the x, it's possible to also rewrite this simply multiplying by a negative everywhere as x squared minus 2xy minus y squared is equal to c. So either or. Regardless, again, any of these formats, they're all completely equivalent, whether you just leave it like this, or whether you leave it like this, or whether you leave it like this. As far as I'm concerned, on an exam, there is no difference. I'd give you guys full credit regardless. On the homework set, they probably expect you to present it in one of the two ways at the bottom for the system to recognize it properly. I think that when you do these problems on the homework, this bottommost one with the x squared minus 2xy minus y squared is what they spit out as their given response, but I think hopefully the other one that's in the standard format should also work. Regardless, that completes everything that I want to go over for this first example problem. Hopefully you guys can see the amount of work I expect you guys to show when you're completing an exam problem like this on the exam. And if for whatever reason, the homework is not expecting any of the answers like I've presented here, let me know. But hopefully this should cover everything that you need to know about these problems. And that'll be it for this video, and I'm going to move on. I'll be making a couple other videos, one on homogeneous equations, as I mentioned, and a couple others covering some problems from the earlier sections, I think 1.1 through 1.4, so that you guys have some example problems covering most of the stuff that will be on the exam.